lectern. And throughout the breaks, feel free to peruse through it. I'll leave it here for the next day or two. Please just make sure that it's still here on Friday.
Right. Good. Then, oh, I can now see. So today we're going to have two sessions, like 2 3-hour sessions on tensor networks, which I will be presenting, both of them. So bear with me as we try to get through this. Before I start, like, who has heard of tensor networks? Who has used tensor networks? Good. So like a very minority of the class. So then this is going to be interesting for everyone. Right. So I'm Lukas. I work at the Flatiron Institute in New York. And just before I begin, let me tell you like a little bit about the Flatiron Institute as a little shameless promotion, self-promotion kind of thing. So this is a foundation that is or was funded by Jim Simons, and it's basically like a university but privately funded for doing all kinds of computational science. And so there's like this ginormous building with 2 floors of astrophysics, 2 floors of biology, 2 floors of math, 2 floors of quantum physics, but it's all computational. And the reason that I'm mentioning this is that there's also a number of opportunities for summer internships, also fall and spring pre-doc positions are available. So you can apply for this if you want to spend like 3 months in New York and do stuff like that. So I'm at CCQ, I'm at the Quantum Center there, and one of the primary things that I'm working on, I mean, there's a variety of different computational efforts there, is the iTensor software. And interestingly, and so this is the brainchild of Miles Studemeyer and Steve White, and then I think currently the lead developer is Matt Fishman. And so we are a team of 4 people that are maintaining this right now. Interestingly, this is not what I will be presenting today, even though, of course, the concepts are the same. And I will go back to my roots a little bit, which is actually from Ghent University. I'm from Belgium. I did my PhD with Frank Verstraete and Jutta Hageman. So this is the team of people that I did my PhD with. And my PhD was on symmetric tensor network methods and using symmetry to really boost those things. And so I want to give you like a little bit of that ecosystem. Good. So for today, I mean, there's a bunch of things that I want to get through, and we'll see how much in detail we can do this. But just as a general layout, these are the topics. But I'll try to keep it a little bit like hands-on, hands-off, like just switching over between the two, mostly because I cannot focus for that long. So, you know, like then you can do some stuff and then I can do some stuff and that works. So I'll just give you a little overview first, a little history, a little background, and then we'll do some hands-on for actually getting to work with these kind of tensor network methods in Julia. And then finally, I want to do like actual algorithms from scratch, give you the basics, to give you some feeling of like, what are the things that we care about? What are the things that we're using? What makes it easy? What makes it hard? I think this is important. And then finally, I want to give you a flavor of symmetries, what that buys us. And so this ranges from computational gains, memory gains, but also I want to highlight that we are able to do fermionic systems with tensor networks as well in this kind of elegant framework that natively incorporates anti-commutation relationships in the methods themselves. Right. So let's dive in. Like, what is a tensor? This is probably like a good question to ask and a good question to answer. And I mean, you might have already heard this very weird circular definition of a tensor is something that transforms as a tensor. And if you are like me, then you think that this is not a very useful definition. And so we're going to throw that right out of the window immediately. And the reason we can do this is that Tensors show up in a ginormous variety of mathematical and physics contexts. And for quantum physics, there's a very specific definition that we can use that kind of bypasses a lot of the complexity that is typically seen in like topics like general relativity. And the main thing is that all of these notions of covariance, contravariance only show up weakly in what we do. And so for the purposes of today, and actually for the purposes of almost the entirety of the tensor network theory, you can really think of a tensor as the generalization of like just an n-dimensional array. So I just have a collection of numbers. These numbers can be a vector if I lay them out in a column. They can be a matrix if I lay them out, well, in a matrix. And if I just keep adding dimensions, I keep adding directions in which I can add numbers, then I get higher order tensors. And so what do these numbers actually mean? If you go back to like what's going on here, I mean, a tensor is just some notion of a linear algebra thing, which is a multilinear function. What does that mean? It's a function that takes in some inputs and spits out a number. And this number is exactly the number that I will put in these arrays of arrays of numbers. And their defining property, and this is kind of like the entirety of the entire field, is that everything is linear. So that means that like if I take in the sum of two vectors, then I will spit out the sum of each, of just taking that function on each of the components. If I scale one of the input vectors, then this just amounts to scaling one of the output vectors. And this should not be that surprising, given that we want to do some quantum physics with it, because quantum physics as a whole really is just linear algebra. Everything is kind of linear, and you just have to deal with the fact that it is linear algebra in a massive exponentially growing system, but it is just linear. And so what that means, like what linearity buys us, is that you can write things down in bases. So you can choose a basis and then define a tensor by saying what is the action of each of these basis elements. And so that is precisely how we typically define these things. Like it's just like, okay, if I choose a basis, how much of this tensor is a component in that basis? And I just put that number there. And so here you can really see that if I have like all of these numbers stacked together, and now I have an order 4 array, this just means that there are 1, 2, 3, 4, 8. Can I count? Cannot count. 16 different basis vectors that span this entire tensor. And so I need 16 numbers to completely specify this. What can you represent with a tensor? Well, basically almost anything. And so, I mean, okay, quantum states is a good example, but like an image is also an example that you can use. So here I have pixels, so a row and a column index that I map to red, green, and blue. And so for every input of this pixel, every discrete input of X and Y, I just assign 3 outputs, which are each of the channels of the colors. And so now I've represented this image, which is the Julia logo, as a tensor. More useful for us, or more relevant, is that any function that just takes in discrete variables can just be reproduced in this exact same form. You just enumerate all of the discrete values that you can have, you assign the number, and you put it in this multidimensional array, and now you have a tensor. And so in particular, like the thing that we'll be dealing with today the most is a wave function of a discrete system. You enumerate all of the different states that you have in your quantum system. You write down the amplitudes for each of these different states, and now you've collected your wave function into one big tensor. Interestingly, like the thing that is very nice of tensor networks is that the quantum circuits and tensor networks almost have this one-to-one correspondence, And I will explain the notation a bit more in a bit, where writing down the quantum circuit notation actually just boils down to writing down a big tensor network. And so the entirety of evaluating this quantum circuit just gives me a tensor again, which is, again, not surprising because, I mean, at the end, it should give you a wave function. There are a bit more surprising things you can do with tensors that we'll not go into a lot of detail today, but I at least want to mention them such that like if you come across this, you see that these are also possible. So a tensor, almost by definition, you need something that is discrete as an input. And so what if you really wanted to do anything continuous? And so, I mean, like we're living in a digital age. Everything is already kind of digitized. So what can we not just do the exact same thing for tensors? And the answer is yes. If you just take a number, like for example, just like I will fix that my range, my domain is between 0 and 1. I can just write down the decimal expansion of this entire range with every number being a discrete value between 0 and 9. And if I do this, I can make a tensor out of all of these different components. And I just say like, oh, for my decimal expansion, every single decimal value is now a discrete entry in this tensor. And my function just assigns outputs to these inputs. Of course, if you do this with infinite precision, you need an infinitely large tensor. But we're used to this from the beginning. Like all of our computers are working with floating point numbers. These are supposed to be real numbers. They're always truncated. So this is just the exact same kind of idea where like, oh, we'll choose some precision that we will limit ourselves to. And then from there, we can start and use all of the nice tensor machinery on these continuous functions.
Does this show up in any situation, or is it just for illustration?
It really does. There's an entire field of the subfield of tensor networks, which is typically called quantics trains, where they encode functions like this. And the nice thing is that like a lot of functions that are smooth or at least reasonably smooth or have a finite number of discontinuities have very efficient representations in this way. And on top of that, you can actually manipulate them quite efficiently. So you can multiply them together, you can add them, you can integrate over them. And so there's people that are doing partial differential equations in higher dimensions with this. There's people that are just doing like, well, high dimensional integration style stuff. So I'm less familiar with this, but there is definitely, like, this is not a contrived example. People are doing this. Something else is more close to what I sometimes do is that you can also choose different bases to expand everything in. And so a digital or like a decimal expansion is one way you can encode a continuous variable. Another way is like if you have some function where the inputs live on a circle or the inputs live on a sphere, you can expand this in a basis set, in any basis set of your choosing. And so, for example, on the sphere, this would be the spherical harmonics. On the circle, you can just expand in sines and cosines. And you can still, as long as you can efficiently truncate this infinite basis set, you can still write down your function now in terms of continuous variables with a discrete finite amount of data. Don't worry about the ugly formula. We will not be needing this today. So there's many, like there's probably way more examples of where tensors show up than I can put on a slide, and also that I know about. But maybe let me like mention some of the important ones. And so like there's a number of counting problems which you can formulate as just evaluating the function like of a large tensor. I'm not saying this is always the most efficient way of doing that, but like you can map these things to each other. Statistical mechanics, like computing partition functions on 2D, 3D grids, very easily map onto how to evaluate large tensors that form a network together. Probability distributions, and that's also where the decimal expansions very often show up. You can sample from a tensor network or from a tensor in a very easy way by just putting one of the indices to a specific value and then evaluating all of the rest, and that marginalizes if you take partial traces, and all of these things very conveniently map onto elementary tensor operations, such that if you manage to formulate these things as a tensor network or as a tensor, you can use all of the machinery that we will talk about today. I already mentioned the integration of the continuous functions. And then finally, there are a number of parallels you can draw with the machine learning community. You'll see also that a lot of the notation is shared. There is some cross-pollination there. You got to keep in mind that one of the important parts, tensors and tensor networks are multilinear. They're always linear. Machine learning methods and specifically like neural network methods need some kind of nonlinearity. So there are definitely shared pieces, but there's also very important pieces that are different. So, I mean, keep that in mind if you browse the literature for that. Good. So you've already seen some of this on the slides. Like we have like tensor network community has a very specific kind of notation, and it's actually like there's some funny part about this where you can kind of think about like as you start as a toddler, you start learning like some basic shapes and some basic notation, and then as you get older, you learn more advanced notation. Maybe you learn how to add things, subtract things, multiply things. Cube roots, square roots, integration. And then at some point, everything gets kind of out of hand. It's no longer tractable. And then you end up with boxes and lines because apparently actual math equations is too hard. And so this is one of those cases. And so basically the idea is that anytime we want to represent a tensor, the only thing we're going to do is we're going to draw some shape, and the shape is kind of irrelevant. We can just use this to indicate some properties, but that's just convention. And for every single index, for every single order of the tensor, we will draw a line sticking out. And so the idea is a bit that like if you draw a line, that means that you can have several different values on that line. And anytime you put a value there, you select one of the components. And so in that sense, if you look at the examples below, like a vector is just some shape with one line. As soon as you fix the value of that line, you have selected one of the components of your vector. A matrix, similarly, is a shape with two lines. If you select the left component, you end up selecting a row. If you only fix the right component, you select a column. If you fix both, you end up with an element, a component of the matrix. Yes?
Do the directions of the lines matter whatsoever, or is it just like a free choice?
It is a free choice in most situations. Sometimes you have to be a little careful, and we'll see that this afternoon in the sense that, of course, I think bosonically everything is fine. You can just move things around. And this is some of the information that you lose by this diagrammatic notation. You have to remember which one is which. But in some sense, we will see that like a matrix and its transpose, you can kind of think of them as almost the same in a tensor network setting, because you will constantly, implicitly be permuting things back and forth in whatever shape is most convenient for you. And so in that sense, it doesn't really matter in what order you draw them, as long as you remember that well, as when I draw this, I meant that the left one is the row space and the right one is the column space. Here you can just, like you pick one and stick with it, but it's just a convention. The notation becomes powerful when we add one small piece of information, which is that if you join the lines, we will use this to signify tensor contraction. And tensor contraction is just the general notation of like, oh, we will sum over the connected index. And so the top left is just, okay, I attach a blob with 2 legs to a blob with 1 leg, also known as matrix vector multiplication. The middle is, well, some kind of contraction with, yes?
How do you distinguish like the top 2 blobs with 1 leg versus, oh, because like if I was just looking at this diagram and it was black and white, for example, it must be color coded?
It can be color coded. You can put labels on it to signify which is which.
So if I had 2 blobs with the left-hand leg, how would that look different than a blob with a left and right leg? Oh, okay. I just answered my own question. Thank you.
Okay. Right. So indeed, you start connecting lines, meaning summation over the connected indices, and you need to kind of remember indeed which lines are which boils down to the same question of like, does it matter which go where? But in general, whenever there's ambiguity, we just put a name on there, give it a color, try to distinguish them. Like it's a notation to signify things. It's not necessarily like the absolute rigorous way of doing this. So let's try this out and then try to describe what is going on here. So like the first one, can anyone tell me like what kind of operation this is?
Dot product.
It's a dot product indeed. Like it's just the inner product between 2 vectors because I have a vector, something with 1 leg on the left, a vector on the right. You just connect them. So the second one is the trace. Very good. And then the third one, you just use your words, describe the inputs and the outputs.
Using a third order tensor to
Oh, is it too much down on the screen?
Dotted with vector.
Yes. Yeah. So the last thing is we start from an order 3 tensor. I will remember next time to put my figures higher up on the slides. You multiply one of the legs with a vector and you end up with a matrix. And so, yeah, like in a general sense, like this, a tensor network really is just this. You take a number of tensors, you connect them together. Yes.
Can you go back 2 slides just for a second? I wanted to.
This one?
The one before this. Okay, no, sorry. I thought I misread the second diagram. Okay.
No worries. I will use this to have some coffee. Right, and so a tensor network basically just means put a number of blobs on the screen, connect them together the way you want, and evaluate the result. What's nice about the notation is that you can kind of immediately deduce a number of things from the notation, which is very hard to do from like an equation. Give me 1 second. Which is that if you just count the number of legs that are not connected to anything, that tells you what the shape of the output will be. So here, even though like I'm not entirely sure what this network is supposed to represent, I know that the result is a vector because, well, there's 1 leg that is not connected to anything. If there would be no legs connected to anything, well, the result is a scalar, just a number. Yes.
Yeah. How do you do like outer products in this notation?
If you, I don't have it on my slides. If you, well, okay, so what would you do if you were designing a notation like this?
Would you like stick 2 things together so there's 2 legs, but you had to like.
Yeah. So if you draw 2 vectors that have legs sticking out and you don't connect them, you can now look at this thing as a whole, and this is now a matrix. So in that sense, like an outer product is just contraction over 0 indices, and so it's just 2 shapes with a leg on each without a leg connecting them. This is the reason why we do this. If you actually want to write it out, you can. This is like, if I give you the equation on the right, it's really hard to know what's going on. Like you have to really start looking at all of the indices. Also, it's very easy to run out of letters. You have like the regular alphabet and the Greek alphabet, and I feel like once you add the Cyrillic alphabet with subscripts for that, you realize that maybe we should come up with a new notation, and that's what people have started doing. And so, I mean, the main idea is just that like you can omit a bunch of these names and make them implicit, and also you can see the topology of the network. Like if I give you like a very large network, and at the end it's just a number of matrices that are all multiplied together, it's not that easy to spot in an equation, and in this notation it's a lot easier.
The previous slide also, is there some rationale behind using subscript versus superscript indices?
That's a good question. In general, no. For the purposes of this thing, like I'm going to probably put my indices up and down, and I am not super careful with this. In principle, yes. Like if you want to be a little bit more rigorous about it, you can think of tensors as maps between vectors and covectors, 2 vectors and covectors. The main point is that we tend to handle that with arrows, and I did not want to burden the notation too much, and I didn't feel like rewriting this equation. So it's a bit of laziness and a bit of, for most purposes, it doesn't matter too much. So for our purposes, we can forget about this for now. Yeah, but I think to give a more in-depth answer to this, the reason why covariance and contravariance, or like typically like upper and lower indices, matter is because tensors often appear as elements of a tensor field, which are defined on some manifold. And then you have to know, oh, if I move around on this manifold, do my entries change covariantly or contravariantly with the basis change? The thing is, we are dealing with discrete functions, so there is not necessarily a manifold that we're moving over. And so therefore, most of that, in a context where there's no symmetries, most of that just disappears and is all the same. Because a row vector and a column vector are just a reshape of each other, and so you can just move indices around without doing anything. Good. Any other questions now that I have this?
Like, are there change of basis? Is that something you can do here? Like,
Yeah.
this is something where covariant contravariant matters, right?
It is, although the point is that like, and that's kind of what I was alluding to before, the change of, like you can use the metric to go between covariant and contravariant. In our purposes, the metric is the identity. So all of the things we do in tensor network methods in general, and especially if you want to do computational things, is that, well, if you want to put it on a computer, you need to choose the basis. And you can definitely choose the basis however way you like. But if you change the basis, you have to change the entries. But it doesn't really matter whether it was an up or a down index in this context. So why tensor networks? If we go a bit further, well, if you think about like these tensors, I mean, I told you a lot about what it was. I didn't actually fix any of the problems. If you start adding more indices to it, if you like have n different spins and you have a wave function, we all know that like you need an exponential number of coefficients to represent this. And so at some point your computer will break, and like that's not what we want. And so the idea kind of is that, well, if we, instead of writing a big tensor, we factorize this thing into a network of smaller tensors, we might actually be able to break like this exponential scaling, because now we only have the smaller components. And anytime we want to evaluate something, we just, well, work with this factorized form and compute our results on that.
So it's like you choose a basis set and then you create a new basis set of tensor representation.
In some sense, yes, and in some sense, no. I think like what's kind of is my mouse visible on this? It is not. The idea is a bit that if you choose a basis, that typically means you've chosen a basis on the open indices. So for my wave function, if you think about the stop thing as a wave function, all of these local Hilbert spaces, I've chosen a basis on. What I'm doing now is I'm factorizing this out into a network, and I've changed my representation, but I have still done this in the same basis, which means that if I, on the top, change the basis on the local Hilbert space of the first spin, I have to actually do the same thing on the bottom, and I have to also carry that out there. So this, like the basis of the actual tensor remains the same. I've just chosen a representation that is more efficient. And I'll elaborate a bit on this in a second. So the idea is that like any time you choose how you want to represent data, there's basically three components that drive your choice. I want something that is as compressed as possible. I mean, we saw this with the polystrings. Like you can write these things out with a lot of resources, but you can also just use a very efficient bit representation. And so here, like the idea is kind of the same. Like I want some way of writing these big tensors as compressed as possible. The flip side of this is, of course, I want something that can represent everything that I want to represent. Because of course I can compress everything down and describe it with a single parameter, but now my degrees of freedom have completely gone. And so, well, I need something that at the very least will be able to span the space of things that I want to be able to represent. And then finally, like I really need something that I can actually work with. Like I can do a very complicated compression scheme that can, you know, like represent anything very efficiently. But if I then have to do any operation on this and have to undo this entire compression to actually measure something, this was all a complete waste. And so the idea is a bit that tensor networks answer these three things, and I'll show you a bit why. And so this is like the standard quantum mechanics scales exponentially. Like if you add more indices, you need an exponential amount of values. And so the idea is a bit based on a singular value decomposition. Has everyone heard of the singular value decomposition? Yes, principal component analysis, very good. So if you look at a matrix, you can compress it a bit by taking the singular value decomposition and truncating the singular values. And so the idea is that instead of a big matrix, I store this big matrix as the product of tall and a wide matrix. And so I have approximated the result. I've thrown away, discarded some of the singular values, but I have reduced the number of coefficients that I have to store. And so actually, let me see if I can pull this up in the meantime. That works great. Has anyone ever done any singular value decomposition on images? So then this will look very familiar, but I think it's very important to see why tensor networks work to begin with. I will put all of the notebooks in the Zulip so you can play around with this later. So the idea is that while things are starting up, as I have said, like if you take an image, you can represent this as a tensor by saying like, oh, it's a map from row and column index to, and in this case, I'll use a grayscale because I just want to use a single number. And so this is a picture of a cameraman. I mean, you can choose different pictures here. And so if you then look at this matrix, you SVD the thing, and you have a look at these entries, you can see the singular values that are here. And something really interesting happens there, which is that typically the first couple elements are very large. Is this visible? Is this large enough in the back?
No. It needs to be, yeah, that's better. No, bigger.
Even bigger?
I have bad eyesight.
Were you happy with this? Well, let me also, instead of showing you the numbers, let me just show you the graph. So you see that like a lot of the weight is concentrated here, and this is like at a scale of 10 to the 2, while most of it is just 10 to the minus 2, so like 4 orders of magnitude away from this. And so you can look at these each of these singular values by themselves, and this gives you like very weird looking images. But then if you rebuild all of these and just layer them on top of each other, you can play around with the reconstruction. And so you see here that with just 12 of the values, I can reconstruct actually almost the entire image. And so keeping in mind that this is a 21-fold reduction in the number of parameters for a very reasonable amount of truncation. And actually, if you play around with how many values you keep, at 40, you would probably not even be able to tell from the back row. And so even like discarding most of the entries, you almost get a perfect result. And this is in general true because of this plot, which is basically telling you like how much are you discarding on not a log scale. And you see that like at the very left of the plot, you basically almost have 100% of your picture. Good. So let me go back to my slides. Does that make sense for everyone?
Is that true for most pictures?
For most pictures, actually, yes. This is a good question. So, can I get out of my, yes. So if you think about what is happening here, basically, if you look at these rank 1 pictures here, what do they look like? Well, every time they take 1 row, 1 column, and 1 weight, and you combine this together. So as long as there's a lot of correlation between rows and like within rows and within columns, this will work very, very, very well. A thing you can do is you can, of course, create synthetic images that don't have this property. And so here, this is what happens if you take a completely random actually also works very well. This is a very synthetic way of creating an image which has a high amount of correlations. And then you can see that, I mean, I crafted this specifically to have a completely flat spectrum. And then, of course, things don't work as well. And your errors are, where are we? You need basically the full spectrum before you can really construct the original. So what's going on is that like if you have some separation of scales, if you have some amount of correlations, basically, if you take any normal picture where there's regions that are the same color, like things are not looking like this, you will usually be able to compress this quite efficiently. Good. Right. So then, like, this is the basic building block. This is the idea. You start from a matrix, and then you just kind of recursively cut along between all of the different indices of your original tensor. And so if you truncate all of these different bonds, you end up with a tensor network that now has significantly less storage requirements. I mean, in this case, you can actually compute it. I went from something that is exponential with the number of indices to something that is polynomial. Because the size of every single one of these tensors in the right-hand side of that equation is just the product of the sizes of each of the indices. And so barring edge effects and like assuming that everything is the same size, you just get n times the local dimension times the dimension of the truncated amount of values to recover this state. Right. So this thing is what we will be dealing with today, which is called the matrix product state. And the idea is that like it's just the large SVD of a big tensor with some truncation. And so it is the low rank subspace of tensors that you can construct. Of course, you cannot construct every single tensor in a low rank way. And so this is something that Stefan yesterday alluded at as well, is that like these are methods that are very general, but we don't actually have a promise that these truncations will always work. Indeed, if you have a flat spectrum, this will just make large errors. But one of the things that are actually really relevant here, both for theory purposes and also for practical purposes, is that if I don't truncate anything at all, and I choose my bond dimension or the dimension of these individual components exponentially large, I do actually I can actually represent everything again. And so effectively or like practically what that means is that I usually have a button or a dial that I can tune. Of course, as all of my components of the tensor network become bigger, everything becomes more expensive. But you can show that if you tune this up and up and up, you will reproduce full accuracy. So there's also a lot of like ways you can do scaling analysis on that and extrapolation procedures to make sure that, well, your calculations actually are reproducing something that you wanted and not giving you just pure truncation results. Yes.
What is chi here? Is that the number of indices you're contracting over in each tensor pair? Or like, I guess, what does the chi here represent?
Yeah, so the chi here, I should have mentioned this before. The chi is what we typically will refer to as bond dimension. It's the number of singular values we keep. So it's the size of the index that connects between the components of the tensor network. And this is indeed the thing that you can tune. If you choose this large, if you choose this exponentially large, you can represent anything. If you choose this small, and in, like at the limiting case, you can choose this as 1. And now you've done a mean field approach of the entire thing, where you're just saying like, okay, this is the outer product of a bunch of vectors. And so you have a tunable accuracy now. Yes. There is no reason to assume they're all the same. And in most cases, they will be different. I did not feel like putting subscripts. Yeah.
Is there a reason to expect that the error is monotonic in the bond dimension, or could it go up and down? Could there be like local optima for?
We will see this in more detail. in this layout, you can show that the error is monotonic. Actually, the important property of the SVD itself is that if you take the factorization, the rank R factorization, this by doing an SVD, this is optimal. And so therefore, if you increase the rank, you get a strict better result, and because you can still get the optimal one. And actually, you can make the claim even more specific and say that the error you make, so the norm, the Frobenius norm between the original matrix and the factorized matrix is exactly the sum of the singular values that you discarded.
Oh, okay. Nice.
So as you start increasing, this error goes down.
Okay, fine. Thanks.
Sorry. Can you go back to slides? You had the dimension of
This one?
yeah. Why is it chi-square? Is it not?
So let's forget about the edges. In the middle, you have a tensor with 3 legs. There's one which is the physical Hilbert space, which I've used small d, and then there's 2 which are the left and right neighbors, and these are chi-squared. And then of course you have some edges, but if n is large enough, you can ignore these. Yeah.
I may be thinking of this wrong, but do you like somehow combine this with bit logic? Because you can imagine this is like also applying a mask on these small spaces.
Sorry, I'm not sure I follow the question.
Yeah. Maybe I need to develop it more. But this gives an air of like some similar conversations that we had recently about that Catherine was talking about bit logic, but this is like applied to something different. Is there a way that people combine these 2 concepts in order to continuously compress information? Well, one is like a compression, but the other one is more like an efficiency. So like you have run time is more efficient, for example, and you have compression. Is there a way that people are using this together?
Yeah, so I mean, if you want to couple back to the state vector thing that Catherine was doing, like at the end of the day, indeed, what we're doing here is we're making a representation of such a state vector that we hopefully can apply gates to in an efficient way. And we'll get to this in just a bit. The idea is that if you think about this factorized form and you now want to apply a gate, like a single side gate to this, you can see or you can hope that instead of now having to touch the entirety of the state vector, I only have to touch one of these components, because I can, and of course that I can do way more efficiently. And that is the entire promise of tensor networks, is that like we kind of write everything down in terms of local tensors, local operators. And as long as the things that we're doing are local, which very often they are, in like at least in condensed matter systems they are, we might be able to retain some of that locality and not have to touch the exponentially large system.
No, yeah, it's great. No, yeah, thank you.
Yeah. So you wanted to ask a question?
Oh, yes. Maybe you're gonna go into this in a second, but is there a reason we chose to make it a tensor train? Like, is there a different topology, graph topology that could be?
Yeah. So thank you. Perfect. So the reason for the train is because out of convenience, like it's a very natural way of generalizing the SVD. You can work with a variety of different topologies. There are reasons to do one or the other. The main driving things that give you that decision is that in general, things that look like trees, so tensor networks without loops, are a lot easier to deal with than tensor networks with loops. And I'll get back to that, or they will become more obvious later. But on the other hand, if you can shape your topology informed by the system that you're doing, you can make things more local. In the sense that, like, to make it like incredibly concrete, the right-hand side of this plot, well, or this figure, which I have put on the bottom of my slide again, is a grid, a 2D grid. And so in that sense, neighbors in both directions are near to each other and they're connected. I could as well decide to make a tensor train, make an MPS snake through this grid. And that works at the cost of now having things that, like have to jump between rows, becoming long range. And so in general, we want to keep some locality, and so that drives that decision. We will work with MPS because these are very stable, very robust, but there are definitely different topologies you can choose.
There's certain topologies that tend to be more efficient computer-wise than others.
Matrix product states are the most efficient usually. So computer-wise, without getting into too much details, anything that has the shape of a tree is way more efficient than anything with a loop. And then following that, anything that has more legs will cost you more. So in that sense, matrix product states are quite efficient. Then there's just the practicalities of the entire situation, where there's a lot more research that has gone into matrix product states. People are doing PEPs, projected entangled pair states, in 2D. I've done a lot of that. Katie is doing a lot of that. It's getting there. We're catching up. But yeah, like that's more of an active research kind of direction.
One of the things we talked about either yesterday or the day before was how much faster it was to do, say, matrix multiplication as compared to vector matrix contraction. In order to not have a loop, at least in what we're seeing on the screen here, you're requiring at least one of these things to be a different kind of tensor, right? So there's rank 3 and rank 2. Is that related to what we said earlier? Like, is that a slower problem that you have to deal with at least one time in order to get this greater efficiency of not having a looped topology?
It's not really, and there's a number of reasons for this. Like I presented the MPS as like a uniform bond dimension thing. In general, the edges have a lower bond dimension because they don't have any correlations to carry between left and right. And so what ends up happening is that all of the runtime, all of the cost is in the middle of this chain. So the edges at the end don't matter. And you can make this even more explicit you can promote the edges to be like the same shape, make all of them in order 3, but now just put a trivial dangling index on each of the sides of dimension 1. And you can always make or break a connection 1 thing, because that doesn't actually change anything. It's the same as saying that a vector is the same as a 3x1 matrix. Yes, you've not done anything. And then you can kind of see that this is just a cheaper part of your network. And then the final thing that I said is that we want to be able to work with it, and that is kind of why tensor networks shine as a whole to begin with, is that like you can actually efficiently manage these things. And I think someone at some point said this to me, is like the most efficient way of describing the ground state of transverse-field Ising is saying that this state is the ground state of the transverse-field Ising model. I have now completely characterized this state. It's an exponentially large state in whatever size you want. I cannot do anything with this data format. Like these words as a representation fully specify what I want, but now are completely useless. And so tensor networks solve that in some sense because there are a large variety of algorithms for different topologies, for different things that you can do many things with them for many use cases. And hopefully today I'll show you like a brief tip of the iceberg of some of these. Finally, I'll just leave you with like some references of where there's more information on these things. There's a lot of online tools available. And I'll leave this on the slide for now while we can take a 5-minute break before going into some more practical things. Let me put this here.
Like, you know how like here between these two
Mess. That's right. Yes. I knew it started with the neck. I didn't know that far.
Do you have you
So just for concreteness, we'll start again at like 10:05, something like this.
In like a general relativity context, that's it.
Yeah.
Oh, yeah.
I have like this one small from university.
Yeah.
But I think they just sort of assumed that I knew about all this notation and so I'm looking at like revisit these lectures afterwards. Like, oh, that's
Okay, that's cool. Oh, they're also using the Penrose diagrams for. That's a very clever way to represent this.
In order to break something.
Yeah, I think it's cool. I think it's just in my previous lecture they didn't really introduce what it meant, but now that they've just it's just a SVT between the perfect sense, you know.
So you can have infinite transcendence.
Fascinating way to.
So we try to find something. This is approximately.
And like since it is an SVD, I can see how that would be the optimal way to factor a tensor.
Whatever that value is. Of like, okay, these are like, significant.
I think
Many of them are that's good with this bond.
Julia notebook for the second I was sleeping.
Stefan just did it in a Julia file. So were you searching
I was not I listened to the first part of the stuff like your
yeah. Okay. So yeah, Stefan after that did a model with
related
there is a minimal amount of
all that.
That's what you need.
No, I'm doing
Are you saying like you're taking like you're saying this is a waveform and we're dividing it? Oh yeah, then well either B
Like master equation class, which is like obviously
whatever.
Yeah, physics.
I do.
He's right. I mean, I'm sure he'll get into the dynamics or more later. He's actually quite involved in this. Right now, it's just like I'm just going to throw away
So this is a problem. And the idea is, you're familiar with the adiabatic.
Yeah. I called
So essentially,
but then you also have the
I'm trying to solve this to do it
it's just not going to be as good of a simulation.
like essentially create a Hamiltonian such that
Because that's what this is really doing. It's like going from here to here is just to make it.
Which is some sense easier than it sounds. You just encode each constraint into a term such that the constraint has 1 unit of energy if it's unsatisfied and 0 if it's satisfied. So essentially what the back theory says, if I start with some Hamiltonian, I put it in its ground state.
No worries. I do
project with different.
Mostly I was doing
Very
then we so I basically I start at that time
Tensorization
like
is finally the
location
I've seen a couple talks.
routing, constellation, problem and this is what the spectrum
Yes,
is
I'm
like. So
fine.
different state states and ground states.
You want to just be able to like see this
Now changed over to the Tensor.
I'm trying to
It's just
and then this is
So
what it looks like.
Just starting with like.
Yeah, graph networks.
Architecture, protocols, from a your perspective,
So this is like this is purely looking at these eigens.
and then I started my
Slow enough.
I'm actually quite excited about it.
That's great. Thank you. That's really good. That was So for my, I'm not research, so there is the main thing that
Yeah, so
makes
that's it. You have to stabilize it.
that's
That's why it's very wise.
And all the complexity just get and it's the fact that yeah, it's especially hard to do the same thing quantum matters because you know there's intrinsic state entanglement, so you have to it should be intrinsic in the state itself. So we came up with solutions where you can restore this
This is Fedora
distribution so that we restore scalability.
theory allow familiar with distros.
I'm not very, but I'm like this thing is required.
This is the wrong side.
Yeah, like this
Anyway,
why I
you
switched
said
to
this
thing has 8 gigabytes of code running.
It's more
like
architectural level, like
I got a message saying it.
So it's you had to break down all the operations you have to carry out. So then we're doing that.
Sorry.
There you go.
Times.
Yeah, cool. Good, nice to meet you too.
How you get the best
I graduated, I just finished my master's.
Oh, and I think
So you have to solve a bunch of different problems at the same time.
How about you?
So you have to drop any optimality assumptions, but you can find a
Oh,
solution.
wow. You taught me, yeah. Wow, sweet.
Yeah.
Yeah, what are you,
Like, did they
Yeah.
especially
Yeah, I think like that's also
Oh, great. I got
and achieve this since we don't have quantum methods, surprise methods, memories,
Oh, sure.
Research.
I like it
So
though.
it's
I like
mostly
it.
experimental or?
They don't have keyboards conceptual calculations. It's like, ah, shit, you're doing something, sure. Hey, man. So, to see how they, so
This is,
This is a question.
I'm writing simulation software.
I think that I was the question. I start off thinking of something else, and then I went.
Like a unitaries.
So you're entangling to.
So this two modes of vacuum is like
Oh, we
predominantly the unit tensor nonlinear object group processes. These are photonic fields, but
Like it can stay on the other one.
and the idea is we're trying to purify this entanglement. This is a messy
Yes, that's why
entangled
there are
state that comes out
random
of
terms that
Okay, so you're saying that the modes that make up the space are.
Yeah, exactly. Yeah, and that's because, like, if you think of a phase space diagram of a squeeze state, the squeeze state will look like this in some quadrature.
Okay, and like phase space.
Yeah, like I know that there's a lot of people doing.
Yeah, your canonical positioning momentum operators. Optics or like.
I'm familiar with like the quantum mechanics and it's like at some point like I guess like right now because I know like the phase space is kind of the classical thing of like the operators.
Yeah.
I know I think squeeze states minimize uncertainty. Is that or like it saturates it.
Yeah.
Maybe okay, maybe that's right. Okay. And like how and I know like electron, this is might be my main like the electrons become entangled just from the interaction with photons.
Yeah.
So how would the photons get entangled?
So there's a nonlinear optical process that we would draw from spontaneous permutation version, and this is the Hamiltonian of that process, which this didn't tell me much the first time I saw it, so it's easier if I like explain it sort of visually, I think. So nonlinear optical crystals.
Yes, what did you
Weird things that happen, like a photon of one frequency goes in and splits into two photons of lower frequency. And it turns out when that happens, so that's called a down conversion process. When that happens, the two photons that are created are entangled. So you get entanglement for free out of that.
Okay. And then how would you entangle the two photons from the two squeeze states? And
Yeah, so what you can do is you can swap the idler modes on the signal in idler are just what we call the photons that
Oh, sorry.
Oh, he's programmed to you.
Yeah.
So we can do
This one's so
like a
good.
splitter, switch the idler modes, and now we have like
I cannot say.
and then we can take two of these and do a Bell state measurement on their idler modes. It swaps the entanglement instead of being here. Swap the entanglement to be on the outer rings.
That was the last.
And by
But I did not understand the second leg of it.
So like
He explained how
entanglement is between 1, 2, 3, 4,
Less of the time.
and then once you do like Bell state measurement, it swaps the entanglement to
Oh,
1, 2, and
that's
then
very clear.
That was
So like you have one photon, two, and then basically they make a packet.
Oh, this is not the right person.
And I mean the difference between these two packets is at this point.
I was like,
are actually usually modes 1 and 2 will be this.
Oh,
The separation, this would be like an H polarization.
Yeah, no, it's like that gives the wrong one.
And
I think
that's like almost anything you can do.
Yeah,
Anything that has large parameters.
And then so that's also your research.
Okay, so yesterday was like
Yeah. So it's $90.
Yeah.
So she does have a bonus positive if you just go for
Variance matrices. Exactly. And then we transition to
I didn't have it.
I've never seen this. He said my whole day is ruined.
So what are you?
I had
hoping
MySpace
to
videos
do?
given to MySpace and they would have.
allows us to pull the substitution.
He's like, I don't even care what anything I heard. Anything. I don't.
What? Yes.
I haven't personally. hasn't been relevant to my work.
Bad equation that was
Directly.
super unoptimized in
If I
Python.
get, I just want to come up with an
This
idea.
was super unoptimized in Python.
Yeah, like you'll be like, oh, I see the connection already.
Yeah.
My work has been
Just come up with it
converting
because
Python
at the end of a couple of projects,
quite a bit.
finishing my third year. We have some ideas of what to do next.
No, this is my first time.
Maybe if I get some other ideas myself. Explore that as well.
No, it's fair. Very cool.
I guess the second thing is to see if I can collaborate.
This is a
Write some
conference paper.
and stuff.
And yeah, we sped it up quite a bit.
I know here or.
Yeah, so this is,
Because I haven't seen sorry, but.
so if my tensor. So like
Yeah,
this
I
is
mean,
what it
Sounds
was.
like
Yeah, it seems like dudes that at least have
These
done
are just
similar
like,
stuff are the
instructors.
These are classical.
Don't think of.
Yeah, so this is a simulation on it.
Then add.
All right. I think everyone's back. Everyone's well rested, ready to dive in. I posted the link to this repository in the Zulip. So you can find all of the slides and additionally also the notebooks that we're going to walk through for the rest of today here. And they're set up in the same way as before, in the sense that they are Pluto notebooks. And what that means is that we'll start with the tensor primitive ones. There's a bunch of figures here. This is the actual notebook, the .jl file. This means that if you copy this link here, and I'll put it in the Zulip for everyone as well. Into the Pluto like open notebook page, this should open up the notebook so you can follow along. Does everyone remember how to open Pluto? Yes, I will take silence as yes from now on, so shout at me if no.
Please, a quick review is just like.
Sorry, do you want a quick review of how to do it? Yes. So, if you recall, from anywhere, either VS Code, oh, I think it's bigger. Anywhere, either VS Code or your favorite terminal, you can open up Julia. Depending on the environment you're in, you can open the package manager and see what's in there. You'll see for me, there's a bunch of stuff in there. You type add Pluto to make sure that Pluto is in that environment. I have this set up in a special one. So here you can see that I have Pluto. I will put this on the top of my screen. Possibly. So add Pluto. Then I can type using Pluto to load that package into my REPL, which apparently will precompile, which is interesting. And then finally, I will cancel this because I didn't need this. Pluto.run will start the Pluto server for you.
That's about the last stable version, Julia.
So in principle, everything should run on anything. There were some people with some troubles before that we fixed yesterday. This is fixed by starting in the long-term stable version with plus LTS.
Okay, thank
you. And then repeating the same thing as before. Okay.
That is expected.
Good. So then, while the first notebook is more showing than working with it, but keep in mind that you can play around with these notebooks. You can add code everywhere. You can also see what is actually in these notebooks by pressing, like you can see here at the top left, there's this I icon, and this gives you the source of what I actually typed. So if you want to see what's going on, that is one way of doing this. And so like we will just kind of start again, but now more on a hands-on way. And what I want to do today is I want to tell you a bit about TensorKit.jl, which is a package that is kind of, well, my PhD coming to life in a package. And so this is just one of the ways to handle tensor networks or tensors operations in Julia. There are many other things you can do, many other packages you can use, each with their different advantages and disadvantages. So today we'll do TensorKit instead of iTensors, mostly because I wanted to tell you something about the symmetries. But you can also just use iTensors. That would also work. And so let me give you like a small setup for TensorKit and the primary idea about TensorKit. And so we will, again, just not say that a tensor is something that transforms as a tensor, and just make it really concrete that we start from vectors. And so a vector, what is a vector? Well, it's something that is in a vector space, which means it's something you can add with other vectors. It's something you can scale, and everything behaves the way it should, meaning these things are associative, you have commutativity for your addition, there's distributivity for the scalar multiplication and addition, and everything just, like works out the way you want it to. And so the way we handle this in TensorKit and in many other libraries as well is just we start by constructing a representation of this vector space to tell us the structure of the vector we want to create. And for a regular vector space, there's only one really important property that fully characterizes it, and is the dimension, which is just telling you that I want a vector of a certain length. And you can type this in a number of different ways. We'll be using complex vector spaces because of quantum mechanics, but also using real numbers throughout most of today because short output. So basically, we can create objects that say, oh, I will have a vector of this length by either typing the field of complex numbers squared or complex space, and you give it a dimension. Both of these are equivalent. It depends on whether you like Unicode or not. And so, as I said, the property that kind of fully characterizes this is just the dimension. And you can see that the dimension of V is 2 and the dimension of W is 3 as we've constructed them. And so we can use this to create a vector in the same way that you would, create a random vector or a random array in many other formalisms by just saying that I have a vector V, which is a random entry in this vector space. And what this is saying is that I will just give you a vector of length 2. Remember, dimension of V is 2. And I will fill the components with random entries. A bunch of things are printed to the screen, which will gradually become more clear, hopefully. Importantly, we can see the actual entries of the vector here. We can see the vector space we put in the codomain here, and we can ignore the term codomain for just a second. And otherwise, we can see that it's filled with real entries. This might be surprising since we asked for complex spaces. You can fill them with complex numbers as well. By default, we fill everything with real numbers. It doesn't matter too much. And so similarly, there's a bunch of other constructors that you could use for convenience. You can ask for something which is filled with ones, which gives you a vector filled with ones. And then finally, you can also construct something where you just provide the entries you wanted to have. That makes sense to everyone? Okay, so the idea is that, like, even though it's a complex vector space, we cannot actually infer which data type you want to use for the entries. You might be choosing 32-bit, 64-bit, you might be using real or complex numbers. The difference mainly is that you can take real vectors in a complex vector space by just restricting to real linear combinations of the vector space. And so we still allow that. We're not like explicitly telling you that you shouldn't be doing this for efficiency purposes. And here it's just more convenient because otherwise all of these numbers are very long. And so you can fill them up with complex numbers. I think I have the example below somewhere. We'll get to it. The idea is that if I wanted complex numbers, I can say that I want complex numbers, and it will change everything to complex numbers.
I think it says it at the box right there.
Perfect.
By default.
Yesterday me was smarter than today me. Good. So that makes sense. That means if these are vectors, they should be vectors, which means I can add them, I can scale them, I can check that if I do this in various orders, things match the way that we want them to match. Importantly, and this will probably be the thing we will be seeing the most of today, if you add vectors that are not the same size, the computer will yell at you because it doesn't know how to do that. A space mismatch is what is being shown here, which just tells you I'm adding two things in vector spaces that are not compatible. I don't know how to do this. So that's what's going on here. A matrix is the next step. Is just a map from vectors to vectors. So it's a linear operator. And so they are maps between vector spaces. You can encode this as the mathematical term, which is a home space, which is a vector space in and of itself, meaning I can add matrices together, I can scale them together. This behaves the way it did, that you wanted to. But the way we construct this is in a very similar sense. I have a home space, meaning something that goes from V to W, which are the two vector spaces that we had before. And you can see that it prints it out a bit funny. It prints it out in the opposite direction of the arrow that we input. The reason for this is that rows in Julia are on the left and columns are on the right. And also matrices are multiplied to the right. So things map from right to left. This is probably about, like, let's say 10% of my PhD was spent discussing this convention. Please do not talk to me about this. Thank you. We settled on just accepting both, by the way. Like, this is how you solve convention issues. Make sure that every single convention is supported such that everyone is equally confused. So you can see, I mean, we can fill a matrix and it gives you a matrix. You can see that if I draw it like this, V was dimension 2, W was dimension 3. So I get a 3x2 matrix explaining the direction here. And importantly, I mean, it's a matrix, so you can multiply it with a vector and it gives you another vector. And A times V gives me something that lives in W, as the arrows kind of hinted at before. This is also the point where we start discussing things like codomain and domain. These are just the mathematical terms for output and input spaces, respectively. So a linear map just maps a domain to a codomain. And this is exactly, wait, let me see. go here to the linear map. I map the domain, which is V, to the codomain W, and that it gives me the matrix representation of that map. Interestingly, a vector also has a codomain and a domain, and you can see here that the domain of this vector is represented as 1. 1 in Julia represents the multiplicative identity. For tensor products, this is just the vector space of dimension 1. And so basically what I'm telling you is that every vector in TensorKit is secretly a 3x1 matrix. And this makes it such that things are consistent afterwards. And so you can see here that indeed the codomain, which is the output space of A times V, is the same as the codomain of W, both being W, capital W. We can, look at some more interesting linear maps. We have the X, the poly X operator, the poly Z operator. You can create them however way you like. They act on two-dimensional local spaces, so that works that way. That makes sense to everyone? Good. Silence is yes. So then tensors and tensor products. What is a tensor product? Well, again, you can reach back into all of the literature and the definitions. At the end of the day, the idea of a tensor product is just, I want to combine two vector spaces, create a new vector space out of them, and I really, really want this thing to be a vector space. That means it must satisfy all my properties about linearity that I had before. And in particular, you can kind of show that forces you to have all of these multilinearity properties on all of the components. And in some sense, I mean, I listed some of them here. It's just that, well, the tensor product of a sum with a different vector is the sum of the tensor products. The scalar multiplication, you can put this anywhere and it doesn't make a difference. And all of that just means that at the end of the day, I have a representation of something that lives in the tensor product of two vector spaces, which behaves like a vector. We can do this explicitly. Oh, and I don't have my example here. I can do this with vector spaces. And as you recall, this is O times dash O times. And this indeed gives me, well, the tensor product of these vector spaces. Importantly, this thing is a vector space. Why am I stressing this so much? That means that I can create a vector in this tensor product vector space, and this is just a vector. Sure, I can reshape it in a variety of different ways, but at the end of the day, I can just represent this as a vector, work with it as if it's a vector. And I mean, we know this, our wave function is a state vector. We don't necessarily have to talk about this as an n-dimensional array. We typically reshape this into a big vector. And here, someone was asking this before, how would you write the outer product? Like this. I probably have to scroll up a bit. And you should be able to see that this behaves exactly like you would expect from this, in the sense that the first element, where are we? The first element is the component-wise product of the first two, of the first element of both, and you element-wise multiply these things together and reshape into a vector. Good. Because it's a vector, you can again just create random vectors in the tensor product space. You can, do whatever you want with this thing. We'll get into more details later. But that also means that we can consider linear maps between vector spaces again, but where now the components on both sides are tensor products. So now I have a new operator which maps the tensor product V times W to the tensor product W times V. And again, what's going on here? Well, you can see that I have a domain, which is now a tensor product space, a codomain, which is a tensor product space, and both of these are a total dimension 6, and you see that I get a matrix representation, which is 6 by 6. Which, of course, if I multiply this with a vector in this tensor product space, behaves exactly the same. So in some sense, I mean, you can always pretend multiple legs are one bigger fat leg, and split them back up again in however way you like. And this is convenient for what we'll be following. Note that because the tensor product of two vector spaces is a vector space, I can take the tensor product of three vector spaces as well by just first doing the first two and then the last one, or in whatever order you like. And of course, everything is associative. So in other words, V is the same as, and we can make this very explicit. Is this too obvious for people, or are we still good? Silence is yes. As a result, all of the objects we ever have are all just tensor maps. We call them tensor maps because they're both tensors and linear maps, and they're both at the same time. And we will kind of just reinterpret them in whichever way we like for what is most convenient to us at the time. And they're completely characterized by a number of properties, which is, let's start with N1 and N2, which is the num out and the num in, which kind of very obviously tell you how many legs are coming out and how many legs are going in. There's the scalar type, which just tells you what is the type of the entries. There's the space type, which for our purposes now is just always complex space. We'll see some more this afternoon of how to deal with symmetries. And then finally, something we will ignore for now is that these can also live on the GPU. This is Katie's work, Catherine's work. So type of B can be used to, like print out the full type of what this is doing. And now you can see all of these entries. Good. So having this is all useful, but as we've seen, if the spaces don't match, you can't even add them together and everything will shout at you and give you a space mismatch. So how do we then actually start manipulating this? Well, for example, you can't really add vectors in V tensor W with vectors in W tensor V, but as we've seen yesterday or maybe Monday, like in the state vector thing, you can permute some of these indices such that they then fit together. And so here you can see that if I create these two random things, well, I again get this dreaded space mismatch because they don't fit. But I can use a permutation to make them fit together, and then I just get the result that I wanted. And so TensorKit handles this by exposing the odd tensor macro. And at the end of the day, what this is doing is it's just Einstein-summation convention, where you put a label for each of the indices between the brackets, and then it will handle, it will automatically expand into the right code for permuting these things together. If in Julia ever you are curious about what this is doing, there is the macro expand macro, which you can put in front of a macro and it will tell you what the code is that came out. And so here you can see that what it is doing is it's creating a new, it's allocating a new tensor, and then it is adding the old tensor into the new tensor while permuting it.
This is just a syntax question, but what does the colon equal sign mean compared to just the equal sign?
I'll get to that immediately. So in the context of this macro, there's both the colon equals and the equals. And this is just a choice we made. Colon equals means create a new tensor. Equals means put the data in this already existing tensor. So what that means is that if I remove this colon equals here, I will get an error message because T2 permuted does not exist yet. I can add it back. And then, of course, now it already exists. So I can assign into it again. And that works. So this is just a way, if you already have memory allocated, you can now reuse it.
You can be able to say, for example, in the first one, T2 is equals to T2, but with the indices swapped, or would that break? So like, so to like just have that be T2 and then delete the colon, like would that then work?
It will not. Oh, actually, I wasn't sure about this. I was expecting it to break, but not sure how. The reason is that in-place permutation. So basically, what you're doing is like you vectorize all of these entries, and they're just in one big layout in your memory. Permuting this means changing the order. Changing the order by copying it into a different vector while the order is changed is easy. Changing it in place is really hard. Like also to make this efficient is really, really hard. So this will not work. Oh, actually, it will work. Cool.
Shouldn't we try it without the colon? Or?
Yeah, exactly. Oh. That doesn't work because I've swapped the indices around, so now the two spaces are not the same anymore. I can, of course, and this is like what we'll get to in just a second. Plus equals and minus equals work. So the faster way of writing this entire thing would be T2 plus equals T1 with the indices changed. And so now I'm avoiding this intermediate allocation altogether. In general, UpTensor does a bunch of things. Try out what works. We've tried our very best to make it behave as good as we can. There's too many cases to capture, so let me know if things break. Yeah.
So you said this tensor macro also handles Einstein-summation. So if I did like T2 of B, A equals T1 of AB, I times T3 of I.
Yes, we'll get.
Could I do that?
Yes, in a second.
Okay.
Not yet, but in 5 minutes.
Okay.
So it also takes linear combinations, so you can write all of these things out in more detail. Here, I created a new T3, but you could do in place with plus equals, minus equals, trying things out. Before we go to the contraction, let me introduce one other thing, which is that like if I look at a matrix which maps V to W, I can do this thing which if you have gotten some courses in linear algebra might sound familiar, which is I can think about dual spaces as well. And what is a dual space? It's the vector space of functions on vector spaces. What does that mean? Well, if I look at my matrix, which takes in a vector space and spits out a vector space, I can also think about this as a vector in the tensor product of a dual space and a regular space. The dual space is the thing that takes in a vector space, and the regular vector space is the thing that spits out a vector space. And so in some sense, if you really wanted to think about this in like a very rigorous mathematical way, like a map from, oh, my arrows are backwards. A map from V to W, you can just think about this as a tensor or a vector in W tensor V dual. And I've used the the adjoint Julia sugar syntax sugar to denote dual. And it just means that if I switch one leg from one side to the other, the arrow goes from to the left to the right, and we can interpret this as dual or not dual. This is not super important for the rest of this tutorial. It just is important to keep in mind that if you want to swap legs from domain to codomain, they will change duality. And the uptensor macro has a slight extension on just Einstein-summation in the sense that we can put a semicolon to denote where the split between domain and codomain is. And so here I create M2, where now by default the semicolon is secretly at the end. I can put M3 where now I have one space in the, and we put the codomain on the left and the domain on the right. I can put M4 where I have nothing in the codomain and everything in the domain. And if you look at what the spaces and if you ask for, okay, what is the home spaces that are living here, you can see that M2, M3, and M4 have this shape. And in particular, you see that if I start from something that is W tensor V and then W, if I move everything to the left, I end up with a dual here. If I move one of them to the right, I end up with a dual here. And so as things move between codomain and domain, you get dual flags with respect to where they came from. I would recommend playing around a bit with this. It will become slightly more obvious as that continues. So why do we care about this? Well, I said that tensors are matrices and tensors are vectors, and we want to switch between like how to deal with that. And this is exactly kind of the thing that like TensorKit is doing for you all of the time. But you might want to change the partitioning in how you actually want to matricize. And so this entire repartitioning deal is exactly, okay, I choose that I choose these two indices to be on the left and this one to be on the right, and then now I will represent this as a matrix. And so here, to make this really, really explicit, what I can do is I create a tensor map, and I just filled it with the entries 1 to 18. And you can see that how they are laid out in memory. Like it makes a matrix in that order. And so if I repartition, also known as reshape, what is going on? Well, the entries slightly move around. So you can see here I have two columns, a 6-dimensional column, 1, 2, 3, 4, 5, 6. And here you can see that they are stacked column-wise next to each other. And so this completely is the same as repartitioning and permuting arrays, just with a little bit more of like a mathy syntax. Finally, as was already hinted at, we can use this to do actual Einstein-summation and write contractions this way as well. And so basically, the entire syntax carries over, repeated labels will be contracted over, and non-repeated labels are open on the left. And so the way you would write these various different contractions is has examples here. There's some more examples on that. Is this clear or more or less clear for most people? Silence is yes, great. You're a great audience.
Is there a function to make these plots?
These figures? Yes, it is called Claude code. Yes. There are on a more serious note, there are libraries, software tools available to do this. Most people tend to use ticks for publications or manual labor. If you ask 5 different people, you get 6 different answers. Yeah.
How efficient is this Einstein contraction? Because I know that I'm just coming from Python, then normal matrix multiplication is typically more efficient than writing it in Einstein contraction form, even though you can do that.
So this is part of a lot of work that Katie and I have done as well, is like, how do you do this efficiently? The reason matrix multiplication is a lot more efficient is because people have spent 30 years optimizing this, and you can use BLOS. And so the default way, and also what is happening here, is actually we are doing the permutation to reshape, to like form the matrix, then use BLOS, and then finally permute back. We did a bunch of benchmarks. We tried to come up with better schemes. The main problem is that the problem space is huge, right? Like you have to deal with, let's say, n legs on the left, m legs on the right, where you now contract any combination of them in a variety of orders that matters, and that changes how you would approach this. So writing a dedicated kernel, as you've done with the state vector stuff, tends to be easy to beat the general case. Writing a general kernel that does all of the cases, we have not been able to do. In general, in the tensor network community, the sizes tend to be large enough that the permutation doesn't end up mattering. The idea being that the actual contraction scales as n cubed, the permutation scales as n squared. So as long as everything's large enough, you only end up with the matrix multiplication, and then you're happy to use BLOS. Thank you. Very happy to go into way more detail than this if you really want to, but something which is important, which might not be obvious, is that you can write this thing out in whatever order you want, and it will contract it. The order of operations does not change the result. But up to machine precision problems because of rounding errors. But like typically, if you compare these two contractions, they're written in a different order, nothing changes in the result. However, and this is important, if you look at the number of operations that have to be done, this can actually very dramatically change. And you can write this out with pen and paper. If you do the multiplication of 2 matrices and a vector, you really want to multiply the matrix with the vector first, and then the second matrix with the vector. And we can measure this. You don't have to believe me. And so what I do here is I create this double matrix vector product in 2 ways. And you can see that tensor will respect parentheses. So you can use this to dictate how it will go. Interestingly, in Julia, always profile things by defining them in a function, and then also always profile things after you've compiled them, because the first time, otherwise you might just be measuring the compile times. And so after I ran them once and then I timed them, you can see that one of the orders takes order 0.3 milliseconds and the other 40. So that's a ginormous difference even for this simple result. You can do this in more general cases for arbitrary tensor contractions, and you can evaluate what is the optimal order. This is, in general, a hard problem. Like the best thing you can do is just exhaustively go through all of the options. We won't need that here, but you can keep that in mind as we write down contractions a bit. Can use parentheses to change the order. Can also, like the tensor network community has done this thing where like, well, maybe parentheses aren't the most legible if you have like 7 tensors with like 7 nested parentheses. That doesn't really work that well. And so what we have done is, instead of using like these labels, A, B, C, D, whatever you like, we give integers to give some of these a meaning. And so in particular, you can use ascending integers for the contracted legs and descending for the open ones. And then what will happen is that the contraction will happen in ascending order of the integers. And so this is exactly the same code as before. I now changed the labels for integers, and of course the same thing still holds. You can also see that there's a little bit of variability on the timings, which is interesting.
How do you access the element wise?
So what's important here is that this is toy notation. So I'm not actually accessing any element. I'm just using this to mean subscript 1, 1, 2. So it's a toy notation where these are just interpreted as labels. There's not actually any indexing going on.
If you want to make it negative for it.
You can do that, but the difference is that this tensor macro is something. So a macro in Julia is something that takes in code, transforms it, and writes out different code. And so in this case, we abused the notation of square brackets and reinterpret it in the context of this macro as assigning labels to indices. If you do this without the context of a tensor, it's just regular indexing.
This micro, but I want to do like element one, so control over element stuff.
Right. So let's say that I have multiple A's. And so here I want to use the first one, and here I want to use the second one, right? This is something you might want to do. What will happen is that a tensor will only use the last thing to recognize the labels, and then the rest will just be evaluated as regular Julia expressions. Don't do this. This is like horrendous code to read, very confusing. You probably shouldn't. That is to say, I usually do. Anyways, I'm saying this because making that work, making that macro work with this is a mess, but it does work. So it's kind of cool in some sense. Finally, something that is important is that this is a macro. What does that mean? This is evaluated before any code is really going on. This is at parse time because it's taking in text and spitting out text. What does that also mean? I can't really programmatically put a variable in there. Like if I wanted this one to be a variable, if I put, a variable name there, it will interpret it as a label. So you cannot just be like, oh, this is the variable v, and I mean the value that was stored in v. So that doesn't really work. So there is a neighbor or like a cousin of this function, which is called encom. And that one, you can just give a list of tensors and then a list of indices, and it will contract everything together. And so these two are doing the exact same tensor network contraction. And you can time them again. And so what's the difference here? Why is there a difference in timing? Which is actually not the difference that I wanted. So I'll just rerun this. Good. So now, always benchmark with more than one run, notes to self. There's a small difference between the two, which is boils down to exactly this difference in information you have. The tensor macro knows at parse time what the contraction is that you're going to do, which means that it can evaluate, oh, you're going to contract this one with this one with this, and it also means that it knows what the shape is of all of the outputs. The mcon function is a function, so this means that it actually has no way of knowing what the shape of the resulting tensor will be, because it depends on how many negative values were in this in this list, which it cannot know at compile time. And so this means that the second function is type unstable. This doesn't usually matter, again, because our tensors are big enough and these things take enough time. But if you want the best performance, you probably need something that avoids with that type instability, that avoids that type instability. And that's also like this difference in allocations is exactly Julia's compiler being like, oh, I don't know what the types are of all of these things, so I will have to put them in boxes and allocate more memory for that. You can also see that it's doing a little bit of recompilation, which is, again, because it doesn't know the types of what is going on. Good. Then I have one thing left, which is factorizations. And actually, we have all of the components to do this if we know how to do this for matrices. The idea being, if I take the SVD of a matrix, I get 3 matrices out. I already know how to interpret any tensor as a matrix. So I can just use the matrix representation of M, do the SVD, and get out the correct answer for that. And so you can see here that, well, if you were to write out the spaces of all of these things, they should match the expectations. So also let me put them in a different order. The space of U is 2 legs on the left, 1 on the right. You can see that here. The space of S, it's a matrix, so it has just 1 index on the left and 1 on the right. And then the space of V is again 1 on the left and 1 on the right. Interesting things to note here. If I have more legs, does S ever end up with more legs? Does anyone know this? Is there ever a situation that I can have S as not just a 1-1 matrix?
If you're doing an SVD of like a non-square matrix, then wouldn't you end up with S being, well,
if you remember, M is not square.
Mm-hmm.
The answer is no. In principle, the idea is that, like, what is an SVD or what are these decompositions? You do a rotation, you then do a scaling, and then you do another rotation. And so basically what's happening is that you take the tensor product space as a vector space, you do a rotation on this, and you end up with this new basis, this new vector space, and you don't actually have a way of giving that structure. I mean, I can afterwards say like, oh, I will now reinterpret this 3-dimensional thing as a 3 by 1 by 1 dimensional thing. But a priori, there's no reason why this tensor product thing should survive here. And so basically, this is just creating a new leg in between. And so this new leg doesn't really have any of the structure, and therefore there's no real way of giving it more legs. Of giving it a tensor product factorized structure. Can ask for the singular values. Something that I mentioned before briefly is that if you truncate this, which we also have a function for, you can give this various truncation schemes. And here I'm saying, give me the best rank 1 truncation of this matrix. And it will also spit out the error. And the error is exactly, well, if you normalize it, it's this value, which is just the sum of the square discarded singular values, which is exactly the error you're making here. All right. And then, oh, sorry.
Is S stored in some computationally efficient way? Because I noticed it was C3 to C3, but it's always going to be diagonal in this case. So is there a...
Yes.
Oh, cool.
Well, let me give you the full one. You can see that it puts dots on the off-diagonal elements. It's not actually storing them.
Okay, so it is like purely storing the diagonal.
It is purely storing the diagonal. We'll then quickly do some. Oh, there is a built-in Julia function as well. Linear algebra. Do I have this loaded? So I don't have linear algebra loaded. Give me 1 second. Where were we? So there's a linear algebra.svd as well. It does the same thing. It does not do the same thing. Huh. I thought we overloaded this. Note to self, fix. But the main difference is that it does not do truncated factorizations. So this is relevant. Great.
Is there a reason we write the last matrix as a transpose?
Yes. This is again a convention thing, but it stems from the way that you actually compute an SV. Like there's no deterministic formula for computing an SVD, so you have to iteratively do this. And the way that this actually ends up being done in like these high efficiency libraries gives you the adjoint of V. So it is more efficient to give you that one. And there's some historical reasons why the name is like this. Yeah. So similarly, we can do eigenvalue decompositions, both the Hermitian and the non-Hermitian one, with Eik and Eik-H. Might have seen this in other languages. There's the full, meaning non-truncated version. You can also truncate this if you wanted to. We'll not really be using this, but sometimes that can be useful. Something which we'll use later is that the eigenvalues of A dagger A are the same as the singular values squared. So you can use the singular value squared of A. So you don't actually have to compute the square if you need this. And then finally, sometimes you want to factorize in a different way or to decompose in a different way, where the only thing you care about is that you have an orthogonal basis for left and right. And this is typically a QR or an LQ decomposition, which is available with left orth and right orth. What's interesting is that orthogonal means that if you multiply with its adjoint, it becomes the identity. What that means in tensor networks is that if you ever get a situation where you have a tensor that is multiplied with its adjoint, you can just get rid of this, which is very beneficial and is exactly what you want. So in that sense, that's why this it is something that turns up quite often. Here you can see that indeed, if you take the norm of Q with its adjoint, and it is the identity, and if you multiply them back together, you get the original. So then finally, I want to show basically the dense state vector thing in tensor network language, or at least in tensor network, in TensorKit language. Before I will then have a small break and then we can go after. So the idea is like, okay, I want to write this Hamiltonian of the transverse field Ising model. Maybe before I continue, who has not heard about the transverse field Ising model? 2 or 3 people. Okay. So this is the toy model that people in tensor networks use. It's just a nearest neighbor model of poly z's on nearest neighbor and poly x's on single sides. And the idea is that one of them wants to align neighboring things, the other one wants to polarize single side things, and you get some phase transition depending on the value of g. Why tensor network people like this one? You can sneeze at this thing with a tensor network and it will converge, which is also why we are looking at this now, and you'll see how this is like really, really efficient. So it's kind of like the easiest model for tensor networks. So we already had some of the operators. Here I have the identity operator on the 2-dimensional Hilbert space. I now want to embed this into an n, like a product space of n tensors. And so here, to create x acting on site I make a vector of n identities. I set the ith one to x, and then I tensor product all of them together. Similarly, for creating z on neighboring things, or even on non-neighboring things, you can do the same trick. You fill a vector of identities, you set the ith and the jth element to z, and you tensor product all of them together. So this is the, like the schematic approach of the operator we're constructing here. And then the Ising Hamiltonian really is just writing out the sum, the math sum of the Hamiltonian in the same way as like some of the math translated to code styles here. And we can play around a bit with this. Don't blow up n, because this is an exponentially scaling thing. We're not doing any tensor networks yet. But we can create a Hamiltonian, and you can see the matrix representation for it. We can find the ground state. We're going to do slightly smarter things than just full diagonalization, which is using some kind of Langchos method to compute just the ground state. So finding the smallest real eigenvalue can be done by just giving the action of the Hamiltonian. And so here what I do is I create a random starting vector, which lives in the n-dimensional tensor product space of the local Hilbert space. I give this to this eigensolver, and then just compute the values. Now going a little bit quickly over this because we will revisit this in more detail. So after my second notebook, and then you can compute from this ground state the magnetization, this thing, which we've seen Katie talk about as well. You can take the dot product of psi, the x operator, and phi, a different state if you want, and contract everything together. Here I'm taking the real value because I'm assuming that you will use this for Hermitian operators. And so we can plot this. This is how the magnetization looks across this 8-side chain. And then finally, and this is kind of the important thing, if we look at this state, you can look at the entanglement spectrum. What does that mean? What is this thing? This is basically the singular values between two halves or between two partitions of the entire system. And so why do we care about tensor networks? Why do tensor networks work? Well, as it turns out, if you compute all of these things, I think I have a plot here, you can see that similar to the images, actually this is a rapidly decaying spectrum. And so in general, you can even make this rigorous for local gapped Hamiltonians. You can show that this will always be the case. And therefore, for local gapped Hamiltonians in 1D, this is the famous area law of entanglement. You can show that the total entanglement entropy is bounded by the area of the cut you make. Of course, in 1D, the area of the cut is constant, and so the entanglement you can have is constant and bounded. And so in particular, you can do arbitrarily large systems, and the amount of entanglement or the amount of correlations between two halves of your system will always be bounded, and that makes matrix product states work very well. I have the same plots for some values of the magnetic field. You can look at this for 5 more minutes. We'll start at 11:20 again. I will ask you to maybe already have a look at the next notebook, which is the TEBD one. I'll again post the link in the Zulip. The reason is that if you can already start running it, then we don't have to deal with the compilation time in the beginning. And then we'll start at 11:20. Yeah. You tell me to stop. Sorry? Oh, because drawing, like, it has n legs. I have to make a choice, and I was playing around with trying to make a dynamic amount of legs depending on the value of the slider here. That didn't work, and then it was late. You know. Yeah, so in general, indeed, you want to be using sparse stuff. We will use structured sparse stuff in just a second, and we'll not use the dense Hamiltonian. This is just, you know, like showing you that you can do dense things with this if you really want.
Do not whatever on that it will do.
Yeah, of course.
As long as that will make.
It doesn't seem
First, this is a times b. It's equivalent to a times x minus 1. So what I can do is if I create that's 3 legs. This will now.
So what do you say in Italian?
Brackets this like that. Something with the The reason why I would say that there's no coordinates of this one is that this is a gauge choice. But you can choose whatever basis or whatever function. There's no a priori way of saying this one is more natural.
I think yeah, so this is just for I think what is with this is being empty and then he's had none of seeing that and then we compare
to say for part because also this one now is just introduction of the that this is what cinema last session I don't know but is happening. This is the last one. Same number to then carry over from the top. That's the oh, what happens? So it doesn't happen. Chinese are done. Oh, this is China. No, they use there is both of it for different purposes. That there is a festival. This is definitely not okay, but I think
so maybe that's like early 2010s.
You can get it. It is not okay.
Oh,
it's not okay. Somebody well placed with this.
Yeah.
I'm gonna set up my notebook first.
Yeah. But I think 2010 is too early. I think 2000 something.
2000 something. I think people are holding smartphone. That's 2009. That's
okay, Habara station. Okay. Festival. Sounds like right.
Really wanted to write it like this. This is not this direct alpha. First, you don't actually want to represent
you know where
yes. I won't be going with CPD today. And the reason is
Of this film is 1.5, right?
it's
yeah.
symmetries. Reason is symmetries. You always have to have this thing.
I'm guessing south.
The charge coming in can still equal the charge coming out.
Am I allowed to Google it, or is this a,
Kind of have a problem.
Oh, right, yeah,
Charge in equal.
Used car center.
yeah, this product knew it was in Wisconsin.
So effectively, that means that you can only have symmetry.
Which year?
It doesn't mean that this is
What is used car? So this one.
Wait, did you get the location right?
No, we have to find out only after the year. So would you say this is like 1913? 1940. Based on clothing.
And evaluating the cells too for these like big.
Yeah, so this is a model T or whatever, something like that. But this is a used car. It can't be 19.
Yeah.
So give like another 10 years or
Yeah,
something.
good 10.
But look at the clothing. Would you say it's 1930 or something?
Yeah, so I think we had to run the Julia.
basically that means that
And if that's 20s,
Zero particles. You specify the key. It's 1950. Oh, and the used car is 1950. 17, 16.
Here, 60 seems too.
No, but the clothing.
I think it's a Chevrolet 1950. Or maybe it's 950.
But if it's a Rolls Royce 1950, that should say it. Then that can't be.
Okay, let's go 1970.
That's too recent.
Yeah, I mean that's
Make it 1950. This is, I think, like World War II.
sure, but
Okay.
Maybe
Yeah.
That's my.
Forget about it.
Yeah, okay, that sounds good.
Yes, let's see.
1951.
Okay.
Just a different field application.
1 year off. We're 1 year into 1950. I was
1950.
and it was this is the station. And we put here. Not bad.
Dang, congrats.
This is
This is a time guesser.
Sir, this is Germany. Or
Could
Netherlands.
Could be.
Oh, Ubright Hotel. This is Netherlands. When is this? Oh,
This is 1920.
no, or this like this is Netherlands. I think this is when Netherlands was.
So
This one I even like the one
Amsterdam?
finding the best representation.
there's no information about anything else. It's not just
Or Utrecht is a city.
And the reason why you do this is like if you're doing this, then doing the chain,
So this is where?
you can never store together.
Like at least the last half.
So there's no workflow where you start from a dense state and you're like this immediate everything is there. So you start from a dense state. And you remember that there is some exponential thing with some Good. Let's start again. Is everyone still happy? Good. Yes, is silence, right?
Accepting, I'm giving it lots of threads and it's like,
So let me give you a small recap. So basically what we did up to now is I gave you a little bit of background on tensor networks and then all of the primitive operations you need to build tensor network algorithms. And then we did some dense thing with this, which is of course not what we wanted to do. This is exactly what we wanted to get rid of this exponential scaling. And so the motivation or the idea is the same as with the images, is the same as with the transverse-field Ising model we saw, is that actually in very many systems that we care about, especially in ground state physics, low-lying excitations, the amount of entanglement, also known as like how flat or how not flat is my singular value spectrum, is bounded, is limited. And so typically, because that falls off rapidly, even though there's an exponential, like in an exact representation, there's an exponential number of singular values, we can discard almost all of them and still get very good results. And so the matrix product state is like kind of the exact first way that you would think about doing this. And so what's important, and maybe like something that the slides kind of don't stress enough, is that you can think about this as a factorization of a full dense state vector. But you keep in mind that we never really start from this full dense state vector and then do singular value decompositions to, like truncate it back down. Because if I give you a chain of 100 sites, this full dense state vector is, like 2 to the 100th elements. So you can never write that down in a computer without blowing up your memory. And so what we tend to do is we start from a matrix product state, and then we try to, like manipulate it and find the optimal matrix product state, while keeping in mind that somewhere there is an embedding in this 2 to the 100th dimensional state vector, even though we never really explicitly want to form it. And so let me like copy over some of the functions of the last notebook, which is just the preamble of this one. To then tell you like what is a matrix product state. And so the idea is just like I make a chain of these local variational degrees of freedom. I call them variational because some of the algorithms that we deal with are variational. And you just stack them together, and you keep in mind that at the end, this if I were to contract everything back together, I get my full state vector. For the purpose of this notebook, we'll use the convention where I will map things from the right to the physical and left. You can choose this however way you like. It's nice if we can all do the same one, but you don't have to. So this convention basically means that an MPS tensor is that type. And then I can define a matrix product state or an MPS as a vector of these tensors. Already something that I briefly said before is that we will use this convention where on the left and right end, we put like a one-dimensional leg just to make sure that all of these tensors everywhere look the same. That makes life easier in the implementation as well. We can ignore the center for now. I'll get to that in a second. So the primary parameter we have, which kind of determines how big the variational manifold is that we're in, is the bond dimension, which basically tells you what is the maximal size of the virtual legs connecting the different tensors. And here there's a slider, so you can play around with this a bit. And so how do we start with this? Well, we just create a random MPS tensor by making MPS tensors and filling them with random entries in the same way as the last notebook was doing. What is important here is to note that there's a cap. Why do I not put the full D by like bond dimension by physical dimension by bond dimension dimensional tensor everywhere? Does anyone know? Why is it a bad idea to put a uniform bond dimension and think about the edges? Yeah. Yes. So why is this? I mean, at any point, you can make a cut, right? And you can look at, like, if you think about my exponential state vector, if I make a cut at the left side, so I have a two-dimensional space on the left and a 2 to the n-1 dimensional space on the right, how many singular values can I have there? 2. So you're guaranteed that at that point, full accuracy is recovered with a dimension of 2. So there's absolutely no point to putting like 32 values there because they're all going to be 0 by construction. And so therefore you have like this profile which from the ends to the middle, you can get maximally 2 to the however many sites you already passed. And that's this function cap here. That makes sense to everyone? Good. You can inspect this and see indeed that if I look at the right spaces of all of the sites, 2, 4, 8, 16 is exactly this maximal size. And I think I capped it at 16, which for this system size is the max. If you go higher, you can go to whatever many you like. What's important here is that I just created 2 to the 75 dimensional vector on my computer. I can, and you can see that, okay, my computer is a good computer, but it doesn't generate 2 to the 75 entries every second. And this is just because of the fact that we have a polynomial representation. And so as long as this bond dimension is limited, this is all very, very fast. Put this back down first for now, but we can play around with that later. So then let's do the first thing you want to probably do with any state, is that I just created a state, I filled it with random entries, so there's no reason why it should be normalized. And in fact, it isn't. It will, I think there's a probability 0 chance that it will be normalized. And so the first thing we can do is we can think about like, how would you compute the norm of this tensor network? And the way we do that is just like, okay, I have a state. How do I compute the norm? Well, I take the overlap of the state with its conjugate. I contract the two together, and I take the square root of that. So I write this out as a tensor network, where now you can see that this top row is my state, and the bottom row is the conjugate. And I just connect all of the legs, where I mean contracting over all of the legs. What's important here is to remember what we said about order of operations being relevant. If I contract along the horizontal line first, what am I doing? I'm first reconstructing my exponential state vector, and I'm then contracting it with the bra. This is, of course, not at all what you want to do, because that scales exponentially. So what we do is we do it in the other direction. We first contract one side with its conjugate, and then kind of zip this through the entire network. And you can show that this kind of algorithm scales polynomially, and in fact, it only scales cubically with the bump dimension. How do you implement this? Well, I start from the left with an identity, which is, like this part here. I contract the middle just by zipping it through from left to right. I could equally well do right to left, like this is whatever you like. And then I close it off at the end. And this is the overlap between two states. And then I can define the norm as the square root of the overlap. So as you can see, for the specific example I had, the norm is this value, so not normalized.
Should we just do the contraction? Other types of.
No. So in 1D, there is. In 2D, there is not. And so this is one of the reasons why things like PEPs, and in general things with loops, are hard, is because you can only approximately contract things. And so then you play the game where you have to compute the approximate norm and work with that thing. So you cannot really, well, it becomes a whole lot more complicated. Here, we can exactly evaluate all of these things. So how do you do an expectation value? I have my same kind of figure here because I didn't have time to make the dedicated one. You sandwich an operator between the states and you divide by the norm. And so how would I write this out? I can just do the same kind of zipping through my, my network from left to right. So I start from the identity. I go from left to right. If I'm exactly at the site where I want to apply this single site operator, I sandwich this in between my MPS tensors. If I'm not, I just continue on. And at the end, I divide by the norm. Squared. Yeah, squared. So the state we created here, I can measure the magnetization of it. And this is, again, very fast. I mean, to the point where like we can play around with this again, right? Like if I turn this all the way up, by the time I scroll down, I hope that this slot is already there. Does that make sense for everyone? Yeah.
Yeah, how efficient is the normalization? Is it pretty straightforward? How it works?
So if you want to do this naively, you can do this thing where you just take the first tensor and you divide by the norm. No. What am I doing wrong? And then if I now reevaluate, well, okay, Pluto is not great because cells react to each other. So this goes in a loop. I mean, the idea is that everything is linear. So if I just take this norm and I divide this out into one of the tensors, or like the nth root into all of the tensors, then now I have a normalized state. I think I'm doing something wrong here, but I don't want to live debug my own code. So I will just leave this for now. Yeah.
Is it the high dimension? Like you have a very large n, so is a random MPS state does it just have a very large norm? Like I'm assuming you're looking at E73 and being like there's something wrong.
Yeah, I mean, like it's a large state. It has random entries. It will either explode or implode.
Right.
Yeah. So in that sense, normally you keep everything, like all of the local tensors normalized. But I mean, we'll get to that in a second, but you can do things like that. And now at least there's some bounds on that. But okay, we'll deal with that in a second. Yes.
Considering you're making like building the entries here, is that you first like build the tensors and then fill out the entry? Well, like if you want to give an a state and you want to then from that, it's full one-dimensional, that's still the efficient.
I mean, if you are given a state, by definition, it's a small one. Because if you want to give me a state, you have to tell me an exponential amount of coefficients in that sense. Or you're going to write it out as a sum of basis states. And you're going to give me a finite number of amplitudes, right? Not exponentially scaling. Because if it was exponentially scaling to begin with, then you probably wouldn't have it. And then I can just write that out, SVD that thing, if I really wanted to. You can sum MPSs. You can make product state MPSs quite efficiently. So if you just give me like a single basis state on n sides, there are ways of constructing that. So in that sense, yes, the answer is like if you have a state that you know how to represent efficiently, then typically there is an efficient tensor network representation of it. Yeah.
But still, I think for N26, it's efficient.
I mean, if it's 2 to the 26, then we're going to spend some time doing an SVD, the first one. And then in general, like depending on the state that you gave me, this might be a high entangled state. So then no. Yeah. So this is definitely a restricted manifold. Good. So let's spend 5 minutes maybe to generalize this single side function to a two-side function. So imagine that you want to do the same exercise, but now you have an operator that acts on neighboring sides. So O has 4 indices. I'll leave you, let's say like 5 minutes, and then I will continue. I'll take some questions in the meantime if you want. And the solution, there's an associated solution notebook as well, so you don't have to worry if you don't find things. in Pluto itself, let me open this one. So if I open the Pluto localhost thing, I can open any. So for example, if you right click that, open link in new tab. No, you can open whatever you want.
Yeah, I get those ones. I'm just trying to relate to this. I guess we take some seconds to space. This argument us. Sure. Like you say in English, what will actually be this is like a zipping thing. Maybe since I'm trying the left end, maybe he means. It's like left end, contract the middle, contract the right end. This the whole point of using matrix product states is you don't have to contract the state. No, that would be exponentially expensive. Well, the point is that you do the computation values this way. So maybe the AI that vibe coded this notebook didn't have this picture in mind when it wrote that. Yeah, that could be true. What you're trying to do is that you as much as say first do all of the
right. So let's have a look at this. We'll do many more of these. So if you didn't find this one, no worries.
I was wondering, is it possible that just for the original expectation value function, you could go through like in English what each line does?
Yeah, of course.
I'm a bit confused about some of the things.
Of course, no worries. So in this expectation value function, let me take this drawing first. So what are we doing? We're going to insert one operator on a single site somewhere. So this is a matrix. Like the way you can really visualize this is like I will just insert a blob here, right? And that's the network I want to contract. And so again, I don't want to contract horizontally because that scales very badly. So I want to contract from the left to the right. So then the way I do this is I start from the left end with an identity, which is just, like the thing that connects the ends together. And then I will just start, sorry,
is when you say the left end, do you mean the top like bit of this diagram here?
I
so
mean,
like it's the left end of there.
I mean this thing.
Yes. So in the expectation value diagram, that diagram is rotated 90 degrees from its representation, right? So you mean like the top?
Yes, or the top or the bottom.
Wait, that was part of our confusing.
The top.
Our confusion. Yeah. So you're starting when it says the left end, it means start at like the top slice of that.
That is absolutely correct. Okay. My bad. top. So that, if you want, I can call it T as well, but okay. So I'll start from the left.
Okay.
Contract through this entire diagram. How do I do this? Let's start with the case without an operator. So if I'm not at the site where I want to evaluate this operator, I just do the exact same contraction as I had for the norm, which means I contract my left end with the ket and the bra. So this is just like this small network of, well, in your viewpoint like this, where everything is connected. If I am at the site where I want to add this operator, I take the exact same contraction, but I sandwich this operator in between. So this is, as you can see, it's connecting with label S and S prime to the ket and the bra, where the middle index by convention was the physical one. So now to do the exact same thing for the, let me check my time, for the two-side case, I just copied over that entire code, which means this has to be top. And then what is the difference? Well, now I have this nearest neighbor thing. So now I want to, again, do this thing where I start from the left or the top. I contract through everything. If I'm not at one of the sites that I want to act on, I just continue. If I am at the sites that I want to act on, I'm going to do the full two sides on the top and the full two sides on the bottom and squeeze my operator in between. And so you can see here, let me try and get that on one. Yes. What I end up with is my left end, operator on side J. If you recall, this is this indexing within a tensor expression that I just said not to do. Operator on side J plus 1. These are connected. This is connected to the left end. This is connected to the next to the next side. And then finally, the S1 and S2 are the physical spaces that connect through the operator to the corresponding things on the bra. And then because I already did the next side, I just skipped that. Is that making sense? Yes, silence is yes, good. There's probably some HR problem with me keeping to repeat that, but okay, let's ignore that. So given that we have a state, given that we can represent states, the next thing to do is, okay, how can I manipulate my states? How can I act with operators on my state? And this is kind of this thing that I was already talking about before, is that if you have this big state vector, you have to touch all of the entries if you want to update it and act with a gate on it. Here, we're just gonna see what happens is that if I act with a gate on this big MPS, if it's a one-side gate, all I have to do is I have to multiply this gate onto my state. I look at where it connects, and I can just replace my local MPS tensor with this contraction. And so if I have to apply an operator to a single site, all I do is I multiply this operator into the tensor at that site. I store this in my MPS structure, and I have updated the MPS. There's a couple things that are incredibly important to realize here. One, the size of my virtual indices has never changed. And in particular, I did not have to do any truncation. So what that means is that a single site operator can be evaluated exactly. And also, it clearly cannot grow or decrease entanglement. We can tell because, I mean, the bonds that are connecting it have not been touched. And these things kind of naturally, one causes the other, causes the one, causes the other. And so I can just do one-side operators for free in this formalism. If you look at the cost of this thing again, this is chi squared small d squared. So this is a very cheap operation. So then, of course, things become a little bit more interesting if you look at like two-side versions, because these are gates that can actually entangle your state. And so the way that we do this, or the method of operations, is that we first join the two neighboring sides together, make one big tensor. Then we apply the two-side gate. And then finally, because we want to end up with an MPS again, we factorize, and you can absorb this S to the left or to the right, or absorb the square root on either side, and you end up with a new MPS again. What's important, and incredibly important to realize here, is that in general, if I started from a bond dimension chi thing in the middle here, and I now apply my gate, the maximal size of that thing here is the local dimension times the bond dimension. So I have a new MPS, which is actually still exact, right? Like as long as I don't truncate this SVD, this is an exact representation of the operator acting on the state. However, if I continue to do this, I will exponentially grow my bond dimension. So in order to avoid that, we truncate the result. We take the truncated singular values, we discard the small ones, and we end up with an MPS typically of the same size as before. Does that make sense? So we'll do another hands-on where we try to write out this contraction and truncation with the primitives that we had before. And then I will release everyone for lunch, and we'll continue this in the afternoon. Also, you can, for now, ignore the second half of the comment. I'll explain this after lunch.
The gate is just an operator. The gate is just an operator on two sides, right? So it's just all this stuff. Yeah. This video after that, so because you were tracked, applied gate tracked, and then a re-SVD. I'm surprised there isn't a more efficient way. SVD is expensive. Here's a big question.
Is this like
I still don't think it was the semicolon separates okay. Right. There's a section. Partitions.
Yeah.
So we know that G is it's like 2 by 2 in the sense that it has two inputs and two outputs, right? Yep. The original 2 qubits and then the after the gate applied. So we can do like S1.
It's two. Sorry. Two. Okay, that makes sense. Yeah.
We'll just do a space. And then we can do S1, S2. That's the gate. See, just contraction side. We can sort of find that.
So psi dot A of I would take it as 1. Yes. What we can make whatever convention you want.
I guess that's.
But isn't it?
Yeah.
I'm still like understand like
This is conception.
it's still be
Yeah, just do like the same.
that you're storing the state, like no order store size as a state. Just
But this is gonna end up as.
That only takes 10 bits, right? Store size.
This is going to need to be have an S1.
Sliced output, right?
There is a small.
You can still have just an A, so like horizontally in the matrix product state, right? Horizontally going this way, we have A coming in, B going out. And then we have psi dot A of I and psi dot A of I plus 1. And then your S1, S2 gate, S1 prime, S2. So we want B to have A coming in, and then S. Wait.
This thing is a more general. So this is strictly more. Everything like this. Like this. Everything like this.
So that's for
but V1, V2, right? Do I need to
Oh yeah, okay.
There's no
I don't know the convention.
the order doesn't matter.
I think it matters, but I don't know how it works.
Left and right.
So then you compute the three of them.
Maybe, yeah, I think.
So A.
We can go over some of the solutions. So just before I release everyone, has anyone figured out how to do this? Has everyone figured out how to do this? Silence is yes, no? Come on, guys. Where are we stuck? Like how stuck are we? Just like there's absolutely nothing on your screen yet, or I'm trying to decide if we should have lunch first and if this will help us understand everything, or if we go over this now. Silence is yes, but yes was not an answer to this question. All right, executive decision. Let's quickly go over it, and then we can go over it again in more detail after lunch. So if I want to apply, let's have a look at the drawing once, one final time. First thing I want to do is I want to write the contraction for multiplying neighboring MPS tensors. Then I want to write the contraction that applies the gate. And then finally, I want to factorize again, so I have back an MPS representation. So I can write this out. My first contraction is I take the tensor on the ith side and on the I plus 1 side, and I contract over their respective right and left indices. We agree with this? Yes, good. The second step is I want to apply the gate. So I take this tensor I just computed, I multiply the gates to the physical indices that I had before, and I store this in a new two-side aggregate tensor. And then finally, I want to be able to factorize this. And so in particular, if I make my matricization like this in the middle of the two physical indices, I can just, I'll put it back here, U, S, V, dagger. Oh, let me just write it like this. Factorize this thing out into its components. And the final thing I have to do is I have to write this back into my original MPS at these sites. Whoops. Live coding is always fun. And so one of them is very easy. If I look at this U, because of the way that it has been factorized, this actually immediately fits in this structure of the MPS. So I can just immediately store it back. And actually for convenience, because S was a matrix, I will absorb it on the left. I can absorb it on the right. We can absorb it everywhere, but I'll just put it there because then I'm already done with this. And here I want to store V. But if you recall, our MPS tensors were defined as having two legs on the left and one on the right. And if I look at this split here, I will end up with a V that has two legs on the right and one on the left. And so then I take out the trusty tensor macro, left physical right, and V was left physical right with the other semicolon. Let me scroll that up a little. And then return the state. I will release everyone for lunch. You can ask more questions either now or in the afternoon.
What's a test here?
Sorry?
What's a good test here? Check that it worked.
What gives me some permutation?
CRAN maybe?
Something like, so we already, yeah, you're right, CRAND. That's not true. Sorry, we have a function for this, right? 2, 3.
It seems like it is the
I will write this out more cleanly afterwards. But the idea is that you can take the expectation value we had before, which is the equation that's here, right? The equation, the expectation value of an operator sandwiched between two states is the same as applying the operator onto one of the states and then taking the overlap with the original state. And so these two values should match. This one. There is a default value here. So if you don't supply anything, it will just be an exact thing. The alternatives here would be, you know, like I can set a maximal dimension there. You can play around with a bunch more settings. We'll show after lunch. Yes.
There was something I probably didn't get in the previous lecture about the semicolon. Because I'm thinking, oh, if I'm doing like Einstein tensor contraction, then like I could just, if I wrote it out on the blackboard, then it would just, the L1, P1, P2, R would just be indices, right? So I'm not sure I understand what the moving of a semicolon does or why we need it and how that's
right.
Yeah.
So when you want to do a factorization, you have to matricize because you have to decide, I will split this into left and right. I will split this into domain and codomain.
Okay.
And so the semicolon is that split. And so if I put the semicolon in the middle here, effectively what I'm doing is I'm writing this contraction, but I'm bending this one of the physical legs to the left and the other physical legs to the right, such that I can then do this SVD where I'm cutting exactly where that semicolon is. And so you will always factorize exactly at the semicolon. And I don't want to factorize to the right of these two physical legs, and I don't want to factorize to the left of them. I want to factorize exactly in the middle because I want to restore my matrix product state form, right?
When you define the, like, I get you would need it then for the singular value decomposition, but if you're doing all sorts of other contractions, is it then a bit more arbitrary where you put it?
Yeah, okay. You can put them anywhere. Also, like, you can do this in 2 steps. You can put it here, and then before you do the SVD, you will then have to tell the SVD, oh, where are you going to factorize? And that will mean another one of these calls. In general, you don't actually have to move any data for this. So there's some efficiency. Yeah. You can do this. It depends on the G. So if this is a gate, which is the tensor product of 2 single site operators, effectively what that means is that if you SVD that, you will have a rank 1 S in the middle. So you can truncate that to be dimension 1. And then indeed, it is more efficient to do it that way. If you give me a general gate, if it's like even just a random Hermitian gate, in the generic case, this will be full rank, and then both will be the same. For gates, you can think about this as how entangling this gate is. I mean, if you think about, well, I don't have this on the slide, but if you think about splitting this gate into 2 things and having a leg that connects between them, and then you have the 2 MPS tensors with a leg between them. If I were to just connect these 2 gate tensors into the MPS tensors first, what you end up with is a double line in the middle, right? And so this is a tensor product of the original bond dimension and the bond dimension of the gate.
Let's say this.
And so the dimension of that middle thing multiplies. So in the general case where this gate was full rank, this doesn't gain you anything. In the case where it was not full rank, it is slightly less than what this would give you.
3 on this side and 1 on that side.
Right. So 3 on this side, 1 on that side.
then
But you can't split that in half.
3 on this side, 1 on that side. Just that line.
Yes.
Yeah, but then you
Yes.
can't do this.
I will talk a bit more about truncation and optimal truncation in a second.
Dimension.
This is an order 3 tensor coming in and a vector. So it would require contraction against 3 vectors, and it would give you 1 vector. But what we want is something that contracts against matrix. Give you a matrix to do the whole, like,
Right.
So I
I
think
think I
that
get it, but
I think for a lot of it, the pulling so much, it's at the fact that at the very end, we wanted to get back into that form.
right. Maybe, yeah. This seems reasonably clear to have lunch.